Hello, my name is Daniel Fernandez. I'm the owner of scienceinhydroponics.com, and today we're going to be doing a new video in my series of videos explaining basic concepts in hydroponics. This time we are going to be talking about conductivity, which is also known as EC, which stands for electrical conductivity, which is a very important concept in hydroponics. So we're going to talk about what conductivity is, and we're going to be talking about how it's measured and some of the assumptions and problems that you will encounter within these measurements. So in hydroponics you have a solution that it's an aqueous solution, so you have some water here. And when you have a solution and you have two electrodes in the water that they are connected to a power source, then you will have charges. In order for charges to move from one electrode to the other, they need some way to jump this barrier. So there needs to be some way for electrons to go into something here and to come out of something here in order for the circuit to be closed. So regular water doesn't have a lot of these charges in solution, which we call ions. And in a hydroponic solution, though, we do have these ions present as nutrients. And these ions help transport these charges from one side to the other. We introduce an instrument here to measure how easy it is for these charges to get across this gap. And what we measure here is the electric resistivity, so how hard it is for charges to flow. Now, it's not resistance, but resistivity, because it's always measured across electrodes with a defined area across a defined distance. So it's not just a resistance of the specific measurement, but it's a resistance across a specific distance for electrodes of a specific area. And this is then mathematically the inverse of this. The inverse of this is what we call the electrical conductivity. And this is measured in millisiemens per centimeter. And this per centimeter is per centimeter of distance between the electrodes. So what determines if conductivity is going to be bigger or smaller? Given the concepts I just explained, you could infer that, which is correct, that conductivity depends on how many ions you have, because, well, the more ions you have, then the easier it is for charges to flow in the concentration regimes that we have in hydroponics. But it also depends on which ions you have, because the conductivity of different ions is not the same, because different ions have different sizes. So they move, some of them move slower, some of them move faster, some of them transport more charges, some of them transport fewer charges. So the conductivity will depend not only on how many ions, but on which ions. So in general, more water leads to a lower EC, and more ions leads to a higher EC. Now, what happens if you have a solution 1, let's call this, you measure the conductivity of a solution 1, and then that is equal to the conductivity of a solution 2. Well, given that conductivity not only depends on how many ions you have, but which ions you have, it is not necessarily true that the ions of the solution 1 are equal to the number of ions in solution 2. So this is not necessarily the case. And this is what causes a lot of confusion in hydroponics, and some of the things that I'm gonna try to clear up. So let's talk about TDS, which is a very confusing thing in hydroponics. TDS, which stands for total dissolved solids, is a way that your EC meter has of measuring conductivity. So conductivity, your EC meter will give you a measurement in millisiemens per centimeter, but it will also give you ppm measurement. That is what we call the TDS. So these are ppms of what? What does this TDS measurement actually represent. So imagine the following. We have a solution that is made up of potassium sulfate, which is a fertilizer, and we prepare it to be at 100 milligrams per liter, which is 100 ppms. And then we have another solution, which is it's a solution of potassium monobasic phosphate or monopotassium phosphate, and we prepare this also at 100 milligrams per liter, which is 100 ppms of this salt. Now, what is the TDS going to be? Total dissolved solids, you would think that this measures the total amount of solids dissolved. Here I dissolved 100 milligrams per liter. Here I dissolved 100 milligrams per liter. So if I call this TDS1 and this one TDS2, are these two going to be the same? I mean, doesn't total dissolved solids imply sort of that they should be the same? Well, in reality, what we have is that TDS1 is not the same as TDS2. These two are not the same. Why? Because conductivity depends on how many ions and which ions. And here we have potassium ions and sulfate ions, and here we have potassium ions and we have these hydrogen phosphate ions. The hydrogen phosphate ions. And these two are different. These conduct electricity different, but not only that, but because of their molar masses being different, we have a different number of ions. So not only are the ions different, but their actual number is different. So how can two solutions which have different numbers of ions and different types of ions have the same conductivity? Well, they don't. That's not going to happen very easily. So what happens is that the TDS is going to be different. So what is this TDS and why is it in your EC meter? What's the entire point of having that measurement if it's so confounding? What does that tell us? So this measurement of the TDS was actually invented because chemists were looking at tap water and different sources of salt water and fresh water, but specifically tap water. And what they noticed is that tap water mostly has sodium, calcium, it has sulfate, it has bicarbonate, and it has chloride ions. So they looked at water and they noticed that water has these things, and they said, well, most water sources have the same thing. Couldn't we just measure the conductivity of water and get an approximate measurement of what the amount of salts in them is? And then they created this TDS measurement as a way to approximate this. And they defined a pattern which is 100 ppms of a solution that contains 20% solid, So you have 1000 ppms of which 20% are sodium chloride, 40% are sodium sulfate, and 40% are sodium bicarbonate. And this has a conductivity that's 1.417 millisiemens per centimeter. And this is why you get that in some meters, 700 ppms TDS is approximately 1 millisiemens per centimeter. Because it's talking about this pattern. And then some people who were not looking at tap water, but who were looking at seawater and sources of water that were closer to the sea, then said, well, this pattern does not work very well for us because it really does not represent what we're looking at. So we're just going to create a different pattern that is going to look instead at 1000 ppms of sodium chloride. And then this has a conductivity of around 2 millisiemens per centimeter. And then we're gonna say that around 500 ppms TDS is approximately 1 millisiemens per centimeter. So what does it mean when your conductivity meter measures 100 ppms TDS? Well, if it uses this pattern, then it means that the conductivity of your solution is equivalent to a 100 ppm solution of this pattern. And if you have this pattern, if your conductivity meter uses this pattern, then it means that the conductivity of your solution is equivalent to the conductivity of a 100 ppm solution of sodium chloride. So as you can see, nothing to do with the actual total dissolved solids, but it's total dissolved solids in very specific contexts. So this TDS measurement is very confusing and useless in hydroponics because it does not relate with dissolved solids at all. It does not relate with the solids that we dissolve because these patterns have nothing to do with hydroponic solutions. These patterns are meant as approximations for tap water analysis or for seawater analysis, but they have nothing to do with hydroponics at all. So what are some things that are important in terms of conductivity in hydroponics? Well, the first thing is use the millisiemens per centimeter, which is the actual measure of conductivity. No TDS. Why no TDS? Because it's confusing. Which pattern are you using? Why are you using it? What does that have to do with this? If you measure 100 ppm TDS, does that mean that it should be 100 ppm of fertilizer? No. So no TDS, because it's confusing in hydroponics and it really makes no sense at all. So the next thing is, do not compare EC of different products. What do I mean by this? The conductivity depends on what? How many ions? Which ions? If you have two products that have different compositions, then comparing the EC of one product with the other product makes no sense. You, for example, have used one fertilizer and you use it at 1.5 millisiemens per centimeter. Does that mean that every product you use should be used at 1.5 millisiemens per centimeter? No, because the same number of ions of product 2 could give you a higher EC or a lower EC because the ratio of the ions and how many they are will be different. So do not compare EC of different products. And third, determine your own EC targets. So what you should determine is this. What fertilizers do you want to use in which quantities? What nutrient ratios do you want? Then once you decide the concentrations that you want, do a small scale preparation and find out what EC that gives you. People in hydroponics usually approach the problem the other way around. They think of an EC they want and then they add nutrients till they reach that EC. That's the wrong way to approach this. In reality, what you want to do is figure out which nutrients you want in which proportions and then figure out what EC you should expect for that specific mix so that you can actually prepare a solution that has the exact composition you desire by adding those substances. So a small scale preparation that is done very precisely, as you can see in some of my other videos, with the exact salt concentrations that you want to figure out what the EC should be, and then a large scale preparation that reaches that EC will have that composition, and then you are doing things the right way around. You are calculating what you want, then figuring out the EC, and not the other way around, because the other way around can be wrong. On the internet, many people will tell you you need to run an EC of 1.2, 2.5, 1.8, whatever. That might apply to a single product or to some mix of products, but it does not apply universally. Why? Because conductivity depends on how many ions and which ions. I hope this introduction to conductivity is very useful to you. Please remember to like and subscribe my videos. It is always makes me very happy when you guys like and subscribe, and don't forget to comment if you have any suggestions about other video topics you would like to see. I would be very happy to make some videos for you about those topics. Thank you very much again for watching my video. See you on the next one, and bye bye.